Okay, coming back from that visual, I'm going to switch gears instead of a skateboard on a track. Let's just keep it simple. If we were in class, I literally would have brought a tennis ball. Let's say we have a tennis ball and we're holding it up high above the ground. So ground and a tennis ball up here. The two questions we're going to have to ask ourselves over and over again for this are, what is its height? Is it up high or down low? And what is its motion? Is it moving or is it sitting still? If we've got a tennis ball held up high, um, little physics kind of cue there. The fact that it's up high, that's going to mean it's got gravitational potential energy. The fact that it's held, what that means in physics is it's not moving, as opposed to like if I said a tennis ball is thrown, then the tennis ball would be moving. If it's up high but not moving, it's just got EG. As the tennis ball falls, so kind of later in time, as the tennis ball falls, we're going to talk about that split second before the ground slows it down and adds a force and stops it. As the tennis ball falls, it ends up down low. So that means it doesn't have any EG anymore, but it's moving. So it's got some EK. So in this situation, something starting off up high and not moving, since it started off up high, it started off with gravitational energy and it converted it as it fell, all those joules turned into kinetic. Often in energy, instead of drawing it as in like an equal sign right off the bat, it's often drawn as an arrow, almost like a chemical reaction, kind of showing you the direction. So it started with gravity energy and it ended up with kinetic. Another thing that physics people sometimes do is they put a little apostrophe on the second one to kind of show the change in time. So it started off as EG and then later in time it was EK. If we put some numbers to it, let's say our tennis ball starts off at rest, so it's held 2 meters above the ground. How fast is it going when it hits the ground? We could go back to week one and those crazy equations we practiced. We could use one of those crazy equations. We know the D, we know the A is 9.8. We could do one of those, or we could do this one, I think, easier with energy. It starts off up high and not moving. So that means it starts off with just EG. Later in time, it ends up down low and moving. So that means later in times it ends up with kinetic energy. So exactly what we just talked about, EG into EK. EG is mgh, EK is 1/2 mv squared. What's cool about conservation of energy is the m's cancel out. So we really just have GH equals 1/2 mv squared. G is 9.8. The H I made up is 2. 1/2 of, I don't know, squared. A little bit of algebra, 9.8 times 2 is going to be around 20. Then we got to multiply the half over, so that's like multiplying by 2 again. So our v squared is going to be pretty darn close to 40. 39.2, double check a calculator, which means square root that. We're getting a v of, I got 6.26, and that's in meters per second. All right, let's try another one. Let's say we've got a roller coaster cart up high at the top of a hill and at rest. So we got a roller coaster cart up here. Oops, that's terrible. Let's try that again. We got a roller coaster cart up here. There's you on your roller coaster, up high and not moving. Then eventually you end up down here and you're going to be going quick. I want to know how fast are you going down here. Oops, that little apostrophe means later in time. It looks like a completely different question, but we're going to ask ourselves the same questions. At the start, when the roller coaster is over here, is the roller coaster up high? Well, yes, the roller coaster is up high, so that means it's got EG. At the beginning, is the roller coaster moving? Well, no, the question said they were at rest, so no EK at the beginning. Later in time, The roller coaster is down low, so that means no EG because it's at the lowest point, kind of like a H equals 0, but the roller coaster is moving, so it does have some EK. So it looks totally different, but in a way, the question is exactly the same. The EG is converting to EK. The MGH equals 1/2 mv squared. M's cancel out again. Another plug and chug, just this time we have different numbers. 9.8. Height I made up was 24 equals 1/2, I don't know, squared. Gonna need a calculator for this one. 9.8 times 24, whatever that number is. Then we gotta double it. 9.8 is pretty close to 10, so it's gonna be like 10 times 48. My calculator gave out 470.4. Then when we square root it, rounding it off to 3 digits, I got 21.7. Do your calculator work, make sure you agree. But our roller coaster will be going 21.7. All right, one more, and then we'll switch it up a little bit. Let's say, switching around a little bit, we got a bowling ball, back to a bowling ball. We got a bowling ball up high. You drop it, and as it's making contact with the ground, just before the ground slows it down, it's going 4.85 meters per second. That's our second speed. We can figure out the height it was dropped from. I'm gonna pause, take a sip of coffee, see if you can doodle what's the energy conversion here. Those two important questions. It started off up high, so it started off with EG. It wasn't moving because it says it was dropped as opposed to it was thrown. As it fell, it got lower and lower until it was at its lowest point, so it means it ended up with no EG, but it was moving, so it had some EK, and we put the apostrophe over there. So MGH equals 1/2 mv squared. Kind of cool in this topic, the m's cancel out. So we've got 9.8. This time I don't know. H equals 1/2 4.85 squared. On the right, the 485 squared, and then the half, I get that equaling 11.76 if I did that right. To get H all by itself, we have to divide by 9.8. It's not perfect, but if I round off to 3 figures, 1.20 meters. 3 in a row, in a way they all look different, but they're all kind of exactly the same. Gravitational energy into kinetic energy. I could maybe make up a different one and like work it backwards and find, well, we did how high, we did how fast. That's really about as far as we're going to push conservation of energy. Make sure you're okay with those 3 examples. I'm going to pause this one, and when we start up again, we're going to be on a slightly different topic, but still conservation of energy.